Alright, so in this lesson we're going to start looking at a term called electric potential. You've probably seen this term before. It is more commonly called voltage, and it actually is given the units of volts. And this is another way to discuss electric potential energy. Electric potential is usually very useful when you're dealing with one of two situations, either a distribution of charged particles rather than discrete point charges, or charged particles that are flowing around, say, charged particles in a circuit. Those are two places where electric potential are useful. The way we define electric potential is we define it as the potential energy per unit of charge. And so I take electric potential energy divided by the charge of your particle, or negative the work done to get it from infinity to that location divided by charge. This is kind of the technical textbook definition, but this is really what it's telling you. So it's worth pointing out that you can get electric potential energy from voltage or electric potential just by multiplying by the charge of the particle. So let's look at how we could use electric potential, or how electric potential and how really all of the terms relate to one another. Now, we talked about Coulomb's law of force, and we defined already earlier the electric field, which is basically a force per unit of area, or force per unit of charge. One of the units for electric field is newtons per coulomb, force per charge. Now, it's worth pointing out there's a relationship between force and potential energy. I should have a negative sign in here, and I don't have it. And I should also have a negative sign in here, and I don't have it. I'm sorry about that. An oversight on my part. In fact, we can clean that up right now. But this is technically negative, and this is also technically negative. Cool. Cleaned up. So here we have electric potential energy, which we looked at in the last lesson, and we just define electric potential as electric potential energy per unit of charge. When it comes to work out the electric potential and electric field are related to one another, really by the same relationship that electric force and electric potential energy are. Negative the derivative of voltage as a function of dr gives you the electric field. So another unit for electric field that you sometimes see is volt per meter as well. A volt per meter and a newton per coulomb happen to be the same units. You can prove that to yourself if you actually kind of play around with the dimensional analysis. So this is, I think, kind of a cool problem, and this deals with a cathode ray tube. For those of you who are not familiar with what cathode ray tubes are, they're essentially glass tubes that you use to shoot electrons, or cathode rays. Cathode ray is basically a beam of electrons. At one time, the cathode ray tube is probably one of the most ubiquitous or common items in American households, because any television prior to the advent of flat screen televisions were cathode ray tubes. There's basically a tube in the back that shot electrons at the screen. So in this tube, an electron is going to be released from rest in a constant 330 newton per coulomb electric field directed to the left. The electron is going to move 2.5 centimeters to the right in this electric field, and we're going to answer two questions. How fast is the electron moving, and then what is the potential difference from the left side to the right side? So, oofta. So the first one that I'm going to use is I'm actually going to use a theorem called work energy theorem. You guys probably remember this. Initial kinetic energy plus work done by your force is equal to final kinetic energy. Remember that this electric field is related to electric force in the particle, because electric field times the charge of the particle is equal to electric force. So I'm going to call the distance the traveled distance r, and so I'm going to say QER, where Q is the charge of an electron and R is the 2.5 centimeters, is equal to 1/2 mv final squared, where m is the mass of the electron. So I can actually solve this out for v final if I wanted to. And so what I do is I plug in 2 times the charge of electron, 1.602 times 10 to the negative 19th coulombs. There technically is a negative sign on it. Electric field, 330 newtons per coulomb. And then there'd technically be a negative sign on either the electric field or the 2.5 centimeter distance, since they're in opposite directions. So those negative signs will cancel out. And you divide by the mass of electron, which happens to be 9.11 times 10 to the negative 31st kilograms. And we get that this electron's really moving quite fast, 1.2 times 10 to the 6th meters per second. It's flying out of this tube. So what is the potential difference? Easiest way to do this one is to say the potential difference is electric field times the distance traveled. And so you get the potential difference is actually 8.25 volts. Because it's the left to the right side and the electric field is directed to the left, the potential difference is actually positive. The potential on the right side has to be bigger than the potential on the left side, and we'll talk about that here in a second. The way I know that the potential on the right side has to be bigger than the potential on the left side is by thinking about how potential actually works and how potential and electric field are actually related to one another. Kind of like how force and potential energy are related to one another. If a force is directed, let's say, downward, like the gravitational force, lines of equal potential energy are parallel to the ground or perpendicular to that force. So here what I've drawn is an electric field which points to the right, and we have lower voltages to the right and higher voltages or potentials to the left. Each one of these dashed lines represents what's called an equal potential surface. What an equal potential surface is, or an equal potential line, is a line which connects all the locations of the same potential. You can actually do this for the gravitational force. It's not all that exciting because your equal potential surfaces or lines are actually spherical shaped around the Earth at various elevations. So if you look at the way voltage and electric field are related to one another, remember that electric field we defined as negative the derivative of voltage with respect to distance. We could also define voltage as negative the integral of electric field dot ds, where ds is really the distance traveled. And we'd integrate this from Ri to Rf. Now if we started a place where potential was 0, then delta V and V would be the same thing, and so we get this equation. In this particular situation, the E dot ds piece actually simplifies down, this whole integral piece simplifies down to E delta x, where delta x is your distance. This would work if you're moving in a constant electric field. Delta x is in the direction of the electric field. If the electric field was not constant, then you'd have to do this. So the thing to point out with electric field is if you are a positively charged particle, you feel a force that's in the direction of the electric field. So positively charged particles would travel in the direction, so if we released a positively charged particle from rest, it would travel in the direction of this yellowish orange line, from higher potential to lower potential, or higher potential energy to lower potential energy. That makes a lot of sense. That's the way objects work due to gravity. If you release an object, it goes from higher potential energy to lower potential energy. The weird thing about electrostatics or electric charges is that we have a second type of charge, the negative charge. And the negative charge behaves exactly opposite of the way the positive charge behaves. That if the positive charge feels a force in the direction of the electric field, a negative charge would feel a force in the opposite direction of the electric field. And so negative charges, when released from rest, would travel from lower electric potentials or to higher electric potentials. So it's kind of a weird quirk, but it is worth pointing out that the potential energy of a negatively charged particle is decreasing going this way. Well, because there's negative potential energy here and more negative potential energy over here. So here's some other common examples of equal potential lines. If you have a point charge, you get these nice spherical equal potential lines. If you have an electric dipole, you either get this weird kind of two sphere patterns if it's two oppositely charged particles, or if it's two positively charged particles, you sometimes will get this weird like figure 8 type shape. If you have two plates of charge, and we'll talk about a capacitor in a little bit, you get kind of your constant electric field, which we actually just did. So last problem that I have, let's make sure. Yep, so last problem I have is this problem here, and I want you to rank the following in terms of work done on a positively charged particle from least to greatest, and all the particles have the same charge and the same mass. And so if we kind of look at this for a second, and I want you to think about it for a second. The two that have the least are the same. Particle 4 and particle 2 happen to have the least work done. The reason is they both have a total change in voltage of 10 volts. This one happens to go up and back, but this one just goes there. The second most would be particle 3. It ends up increasing a total of 20 volts, and the most would really be particle 1. It increases a total voltage of 30 volts. So that's kind of a little bit of interesting things with equal potential surfaces and how we can use voltage to figure out what's happening, or electric potential to figure out what's happening in moving charged particles. What we'll do in the next lesson is we'll look at how do we calculate electric potential from distributions of charges.